Hello, class, and welcome to Average Shear Stress. This is Chapter 1.5 in the Mechanics of Materials. Objectives for today are calculating average shear stress, and we're going to describe when it's accurate. We're going to talk about the limitations of average shear stress. We're going to talk about the difference between single and double shear and how that's going to affect our analysis. And we're talking, and our final goal is to be able to use this information to size bolts and design other connections given a shear stress or an acceptable shear stress level. So let's start with a very, very simple example of simple or direct shear. This is basically called direct shear because it's directly caused by a load here, right? It's not, there's no bending involved. It is just pure shear. We'll talk more about bending later. When we have this case here, what we're going to see if we take a cross section at those two places, right? This is where we're expecting failure. If you have a really short distance that this is spanning, we'll see a shear failure at those two faces, A, B, and CD. And if we take that element out, we're going to see something like this. And we're going to try and figure out what is this tau average, what's the average shear stress at those two interfaces. So we can think about designing that or determining if it's going to fail. So the average shear stress is a very simple calculation. It's not too different than the sigma calculation for normal stress that we did in the previous section. We're just going to be taking the shear, resultant shear at that section, and then dividing it by the area of the cross section, right? And it says section, I want to be really clear, that's a cross section here. Now, one of the interesting things about this, and we'll learn more about this later, is that average shear stress is actually kind of a terrible approximation. Even with a pretty vanilla rectangular cross section, we're going to see more of a parabolic stress distribution. We're not seeing a uniform stress distribution across this. So a uniform stress distribution, to give you an idea, that would be something more like this, where you see a uniform stress distribution like this. We're actually seeing a pretty big change between the maximum and then out at the edges. We're actually seeing pretty close to, we're going to see zero shear stress at that point. For shapes, for construction shapes that we often see, like I-beams or T-beams that are incorporated also into smaller structural elements, we're actually seeing much bigger stress in the middle of the beam and not a whole lot of stuff going on at those outside edges. So actual stresses sometimes are much higher than that average. So you're asking at this point, is this actually worth it? Why are we even talking about this? Why do we have a whole section about this? The reality is it's good enough for analysis as long as we use a factor of safety. Factors of safety will come up in just a second here, but it's basically accounting for extra capacity because we're taking a simpler analysis oftentimes, or if we have higher risk applications. So we can use this for both bolted designs and also welded designs. Now, the uniform shear stress assumption is, it's as an estimate, it's better. The estimate is better, and I'm putting a little footnote here. It still sucks. It's not good. But it's better if those parts are thin or small, very small when they're joined, right? We don't want a large span. We don't want a big old large span. We want a little span here. We want shearing to happen, but we don't want to see a lot of bending in that part when we apply that shear look. A good example that you can see of like what shear deformation looks like, this is kind of a macro scale versus a micro scale. This is a short frame that has definitely failed due to a shear load case. You'll notice that the lengths of those members don't really change, right? The lengths of the columns and the beams across this garage really haven't changed, but the shape has changed, right? Originally, this was our nice rectangular shape, and now we have a much clearer parallelogram shape here. And that's what we're going to expect to see in sort of a shear failure mode. The shape changes, but the size of it doesn't change. What happens is those right angles that we measured before are going to start to look more acute. Let me do it this way. So what we're going to see is these are going to start to look more acute. Start to see it fail this way, right? All right, so let's go back to our volume element model, right? This is how we're going to find something about some arbitrary point P. right? We drew a little rectangle around it, we cut it, and we found out that, okay, if we start looking at sum of forces in the y on this, we've got some stresses drawn on this diagram. If we say sum of forces in the y, well, for these stresses here, we're going to find that that tau yz and the tau prime yz have got to be the same, right? They're got to be equal and opposite to cancel each other out. If we do the same thing for sum of forces in the x, we're going to find that that tau zy and the tau prime zy, so these two stresses here, are also going to have to be equal. And we can take it even a step further. If we find that if we take a sum of moments about x, think about this as being a cube, right? Remember, a cube saying that these geometries are the same. We think about what creates a moment about x. We know that this is not creating a moment about x, and this is not creating a moment about x because they pass through that axis. The only thing creating moment about x is this force here, or this stress here and this stress here. So we think about that, we take that moment about x, well, the two lever arms are the same. Because it's a cube, we know that if this is creating a rotation this way, and this is creating a rotation, and this is creating a rotation, if tau zy is creating a rotation this way, and tau yz is creating a rotation this way, and they're opposite, those two things are opposite, they got to be equal. With the same lever arm, those two stresses are equal. So what we find is, basically, all these shear values for this are going to be equal. This is what we call the complementary property of shear, right? All four shear stresses in these cases, as we go around, these are either directed away or towards each other or at opposite edges of the element. These have got to be the same magnitude. So we can actually simplify our model a little bit in 2D and just say, hey, shear stress, we don't have to worry about whether it's acting along this plane or this plane or that plane. As long as we're talking about this particular plane, tau shear stress is going to be the same. And that's going to become very important to us later when we start looking at designing beams. But this is just something to keep in the back of your head, that there's this complementary property of the shear that says, hey, based on just very simple equilibrium equations, we can figure out what tau is going to be if we know one of the taus.